today, I'll repeat this same lesson tomorrow and you'll hear it for the second time, and they'll hear it for the first time. So that's what we're going to do. All right, so I'm looking at a book, and it's chapter 8. We'll do chapter, it's not 8, 9, and 10. It's actually 8, 9, 15. So don't get ahead of me, okay? Don't get ahead of me. But we'll do chapter 8 first, then chapter 9, then I jump to 15, okay? All right. Here's a nice, what is that? Is that a Lamborghini? Oh, Ferrari. Ah.
Todd would know.
Oh, is he a car guy?
Yeah, Todd's a car guy.
Is that right? I didn't know that. Okay. I'll ask him next period. Now, so they're trying to get you interested in this topic, and this must have something to do with it. And some of these sports cars are made of this light material. Yes?
Could you zoom in a little bit?
Yeah. Okay. Thanks for doing that.
My driver's made up.
Thank you.
Now, so what they're trying to say is, starting with this chapter, see the chapter with chemical reactions, that got you into the real world of chemistry, in my opinion. This gets you in the real world of the chemistry that people do out there. Not the chemistry you do in a classroom, but the chemistry that goes on out there. That's these next 3 chapters. If I had a company and I had something to do with making some kind of a chemical, maybe I make this stuff here. Maybe there's a company in Greensboro that makes, I don't have any with me, the stuff that goes in baby diapers. And this stuff that they make, it absorbs 2,000 times its own weight in water. And so they put it in between 2 liners, and then the baby pees, see, they can soak up a lot of pee. And anyway, it's hard to believe that those people make money. They make a lot of money. You know how many people use disposable diapers? They make a lot of money. Well, anyway, that company has something to do with this next 3 chapters also. And so in the real world of chemistry that goes out there, this idea of stoichiometry, and I never heard that word till I got to college, but it's a funny word, and if you say it, you sound smart. So if you can say stoichiometry, say, what is stoichiometry? It's the mathematics of chemistry. And for the first time, you're going to see remember how I made you balance equations? And you said, well, why am I doing that? Well, it makes it make sense. You had 6 atoms here. At least it made it make sense. But there's another reason. God made those coefficients happen that way. And when you get in this world here, that's the way they work. So if you're a company trying to make something, you have to figure out what is the ratio in which this reacts with that. And if you don't figure out the ratio, you say, well, let's put some of this and some of this. Then what happens is you waste a lot of money. You got it? What if you're supposed to put 100 grams of this and 200 grams of that? And you put 100 grams of that and 500 grams of that, you reacted. Well, didn't you waste a lot of money? And in that world out there, wasting money, here's what happens. If you waste money doing that chemical reaction, and another company says, I can do that same thing, and we won't waste money, then who is going to win in the business world? It costs your company that much to produce this stuff all year. It costs us less. See that? Who's going to win? We are. So the idea of stoichiometry, that is how chemistry is applied out there in the world. Okay, fancy name, it just means the mathematics of chemistry. Again, some of you are going to love this. You're going to love this, okay? Now, in the stoichiometry, we'll talk about another thing called the mole concept, okay? I remember it was kind of weird. A teacher I had in high school, he was kind of young, maybe out of college for about maybe 3 or 4 years out of college, something like that. And I remember he got ready to teach this new chapter, and he said, I want to teach you about these things called ELOMs. And I thought, well, I don't know what ELOM was. And he was trying to tell us what an ELOM was. And later, I asked him, I said, why do you call them ELOMs? He said, well, that's a mole spelled backwards. And I thought if I said the word mole, everybody would be nervous because they know that's a complicated idea. First of all, I didn't know what a mole was. So why would a mole be more complicated than an ELOM? But anyway, that was his thinking. that if he didn't say the word mole, that we wouldn't be so nervous. Really? 10th grade student? I didn't know what a mole was, except animal, a thing in your face. That's what I do. All right, are you ready? Now, you actually know a little bit about the mole world. We did some factor label early in the year. We'll do that again, but I want to make sure the concept is there. And so I want to show you the next page, and you're not going to believe this, but if you were to read this chapter, and I do want you to read it, you know what they start out with? Here's this complicated idea, and the first 2 paragraphs are talking about jelly beans. And it says, it even says here that let's pretend that you own a jelly bean store. Okay? Now let's say that customers come in and they say, well, I would like 10 of these jelly beans. Okay. And you pay your employee $10 an hour or something like that. If they're an adult, you might pay a little bit more. and then they sit there and they go, 1, 2, 3. They count out the 10 and and the person smiles, gives you the money, and goes away. And then all of a sudden the popularity grows and grows and grows. And lots of people are coming to your store to get jelly beans. I am going somewhere with the story, okay? Now somebody comes in and they said, now we got 20 people in line, and this person says, I would like 500 jelly beans. Okay, so you got this person there going, 1, 2, 3, 4, 5, 6, 7. Okay, and the people in line, really? And as a store owner, you're saying, I'm paying $10 an hour for that person to count jelly beans. And look at all those other customers. They don't look happy to me. Well, it's similar in the world of chemistry. In the world of chemistry, by the way, what would you do then? What's the answer to the jelly bean dilemma? How can I serve more customers? How can I count the jelly beans without counting them? How can I count jelly beans faster without counting them? What is it? Yes. Now here's what I do first. Now even though this person only used 10, since it's my store, that's going to be a very important number to me. I'm probably going to take, one night after work, I'm going to take maybe 500 jelly beans. And I'm going to weigh them individually. You get that? And here's what I might get. Here's a jelly bean that's 5.1, 5.2, 5.0, 4.8. And I might weigh 500 jelly beans. And then I would divide that by 500. What would that give me? What would that give me? If I weigh 500 jelly beans and I divide by 500, what am I going to get? The average. Isn't that right? And so let's say the average jelly bean is 5.011 grams. Get it? Now, if somebody says to me, I would like 1,000 jelly beans. I don't want my employee to sit there and count out 1,000. It makes everybody else angry anyway, doesn't it? So what do I want them to do? What's 1,000 times this number? 5,011 grams. I have a balance. You pour them out. I guess it'll be about 5,011 grams. All right, throw another one in there just in case. Bag it up. There you go. Well, but you never counted those jelly beans. You're right. You're right, I didn't. But I know if this is a good number here, and I can weigh them, I could tell you how many jelly beans. And if I did that 100 times, I'll bet out of 100 times, I'm pretty much on. I might have given you a couple extras, couple. Got that? So why is this an analogy for chemistry? Here's where you are in the world of chemistry. At one time, we had no idea what this was made of. We knew it was a gas that put a flame out, didn't it? CO2 makes a flame go away, doesn't it? But we didn't know it was CO2. As a matter of fact, they had a fancy name for like dirty air, or they had some of the air that was not good. And we didn't know what it was made of. And so, do you understand, in the world of chemistry, what do we need to know more than anything else? We need to know how many of these combined with how many of these. You see that? So we need to count atoms. Do you have any idea how big atoms are? Whatever you thought, divide that by about a billion. How big is it? Oh.
Very small.
They're small. Whatever you think small is, you're way off. You're way off. Like, for example, I could probably, in one drop of water, there could be a billion molecules. A billion. Now, each molecule has 3 atoms, so that would be 3 billion atoms. We have no idea how would you count something that small, number one, and how long does it take to count a billion of anything? There's no way we can count them, literally count them. We can't that? We cannot count them. They're too small, and there's too many of them. So what do? How are we going to count atoms in the world of chemistry?
You weigh them.
You're going to weigh them. Now, before they weigh them, we need to have this, don't we? So we didn't know what these jelly beans are. Now, by the way, hey, how many jelly beans had that mass right there? How many? None of them. None of them. This is the average mass, isn't it? So look up here in the periodic table. See where it says carbon 12.011? Or see where it says nitrogen 14.0067? What does that mean? What does that number mean? I'm going to try to teach that to you also, okay? So let's go to, let's see here. Let me go ahead and start my notes here a little bit, all right? What I'm going to show you is I'm going to go in the tiny world. And in the tiny world, and whether you like it or not, I like teaching this way. So whether or not you like it, you're going to hear me this chapter here where you say, in the little world, blah, 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 blah. And then I'll say, in the big world, blah, blah, blah. And if you understand what I'm saying, it makes sense. So what I'm going to do is I'm going to go visit the tiny world. Yeah? I'm going to go visit the tiny world. And in the tiny world, we have, for example, this guy here. And even though we know a whole lot about this guy now, at one time we didn't know anything about water. We didn't know anything about it. Yes. Is that too big? Okay. All right. I think I magnified this, what maybe. Okay. So I want to visit the tiny world, okay? Now, what I want to do is I want to ask this question here. Do you know how much this guy weighs right here? How much does he weigh? Now, it's small, isn't it? He's only made of 1 proton and 1 electron. So he is a really tiny mass, really tiny. And so when I look on a periodic table, I see 1.00797, okay? What does that mean? This guy here, and I taught this to you before, there's this guy, and there's this guy, and there's this guy. There's 3 kinds of hydrogen atoms that we know of in the universe. What would you call these? Same kind of element, different masses. What are they called? What is it? Isotopes. We discovered that there were 3 different kinds of hydrogen atoms, but by far, 99.99% of them have a mass of 1. So let's pretend that I happen to have a hydrogen atom here and here, and his mass is 1. So his mass right here is 1. Now 1 what? 1 gram? No, a paperclip has a mass of 1 gram. How can you say, don't sit there and tell me a hydrogen has a mass of 1 gram? What is the mass of a hydrogen atom? And we had this before. 1 AMU. And what's the AMU stand for? Atomic mass unit. Okay, now, what about the other hydrogen? 1 AMU. Got that? And then they had something that weighed 16 times more than this guy did. And so relative to that atom, I weigh 16 AMUs. So in the little world, what would be the molecular mass. What's the molecular mass for water? What is the molecular mass for water? 18 what? 18 AMUs. Everybody get that? I'm waiting till you. If this doesn't make sense, I can't go on. But does this make sense?
Why is the oxygen 16?
Okay, so if we were to draw it, like here's a hydrogen atom, and electrons essentially weigh nothing, so he weighs that much. But oxygen has 8 protons and 8 neutrons, and that alone would be, each of those weigh 1, and so that'd be 16 times greater. So I'm going to stay with this isotope the whole time, and I'll stay with the oxygen 16. Okay, so anyway, so in a little world, what's the molecular mass of one water molecule? It's 18 AMUs, and, okay, that's pretty small. That's pretty small. Now, here's my next question for you, though, okay? What if I were to give you 100 of these? 100 waters. Let's find out about that, okay? What if I give you 100 waters, then what would be the mass of the hydrogen atoms? Well, let's see. Each hydrogen has a mass of 1. Each molecule has 2 of them in there. You're going to give me 100 molecules of them? So what if I give you 100 molecules of water? What's the mass of hydrogen? Who knows? This is kind of simple, but each hydrogen's 1. I have 2 here, and you're going to give me 100 of them. How many? 200 what? AMUs. Now, what's the mass of all the oxygens in 100 molecules of water? And I need somebody to answer, because these are kind of simple. If you can't answer the simple questions, I need to back up. And I don't think you want me to back up, but what's the mass of all the oxygens here? So don't we have 100 oxygens? Each oxygen weighs 16. So what would that be? For a total of what? Are you okay on that? All right. Now watch what I'm going to do here. I'm going to give you more than 100. I'll give you 100. I'll give you more than 100. Okay, how about, what I'll give you 1,000,000? All right, now what? What would be the mass of the hydrogen atoms in 1,000,000 water molecules? How much? 2 million? 2 million AMUs? And what about the oxygen? How much there? 1,000,000 water molecules. Each molecule is 1. That'd be 1,000,000 oxygens. Each oxygen weighs how much? Each oxygen weighs how much? 16. That'd be 16 million, wouldn't it? All right. Now I'm going somewhere with this, okay? I'm going somewhere with this. So what if I were to give you 10 million? 10 million, wouldn't that become 20 million here and 160 million here? And what's interesting to me, is let's take a look at, I'm going to do it one more time, okay? Now, what if I give you more than 10 million, more than 100 million, more than 100 billion? What if I gave you 6.02 times 10 to the 23rd water molecules? Now, how much would the hydrogen weigh? It would be 6.02 times 10 to the 23rd times what? Times what? Times 2 times what? Each water molecule has 2 hydrogens, right? Okay, so I'd have 2 times that. That's how many hydrogen atoms I would have, but each hydrogen atom is 1 AMU. And you know what I get? Isn't that how many AMUs I would get? All right, so what does it come out to be? Like 12.04 times 10 to the 23rd. Is that right? AMUs. Let's do the oxygen. What do you think about that? What do you think about the oxygen? Okay, I'm going to give you that many oxygen atoms. Thank you. How much does each oxygen weigh? Okay, and if somebody wants to put that in a calculator for me, somebody will put that in a calculator? And you know what? I could leave it that. I would just tell me what's 6.02 times 10 to the 23rd times 16? And as soon as you get it, let me know. All right, go. 6.02 times 10 to the 23rd times 16.
9.632.
One more time.
9.632 times 10 to the
9.6 what?
24. 32.
Now, get ready. This is the big deal here. This is the big deal. If it just so happens, this is a very special number. This is called Avogadro's number. Avogadro's number is one you used early in the year. You didn't know what it meant. But what it says is, if I give you this many, something kind of special happens. Do you know how much, you know what I can say? You know how many AMUs that is? That equals something else. That many AMUs equals 1 gram. It takes a lot of AMUs to equal a gram. And you know what this one comes out to be? 16 grams. Now, let's start again, okay? I started from the periodic table. I said, how much does 1 oxygen weigh? And we said 16 AMUs. So if I look on that periodic table, that little number there, let's say it's 16 for right now, okay? If 1 atom weighs 16 AMUs, what would happen if I gave you this many of those atoms? It would equal a whole lot of AMUs, but guess what it equals? It also equals 16 what? Grams. So I can use that decimal number for 2 things. I can tell you in the little world, what's the mass of 1 oxygen atom? 16 AMUs, right? And what if I give you this many oxygen atoms? What can I tell you? What if I give you this many oxygen atoms? What can I tell you? How much is it going to weigh? 16 what? Grams. That's the big world. Now, there's a name for this. What name is given if I give you 6.02 times 10 to the 23rd of anything? What word is used to say, I'll give you an example. What if I give you 2 pencils? What if I give you 2 books? What if I give you 2 popsicles? Could you say that I gave you a couple? If I say a couple, does everybody know that means 2? Is that right or not? What if I said, I'm going to give you 12 baseballs, 12 donuts, 12 pencils? What's another way of saying that? A dozen? Now, do you think a dozen pencils weighs the same as a dozen donuts or a dozen baseballs? No, I never said they weigh the same. They did have one thing in common, the number of particles. A dozen doesn't tell you anything about how much I weigh. It only tells you how many pieces there are, right? Well, that's what this word is right here. And I'm not going to say the word elam. All right? It's a mole. What is a mole? It's not the mass of anything. It's the number of particles. Well, how many? How many particles? 12? No. A whole lot more than that. 100? No. 10 million? No. How many particles do you need to be a mole? 6.02 times 10 to the 23rd. If I give you 6.02 times 10 to the 23rd of anything, I've given you a mole of it. So the word mole tells you about how many pieces. Now, why is that important in chemistry? Because eventually, didn't we want to know what did we want to know about glucose? What did we want to know about glucose? How did we figure out glucose was this? Somehow, we had to get in the world of number of particles. Because I want to know how many. This is not mass. These numbers are not mass. These are how many carbon atoms combined with how many hydrogen atoms combined with how many oxygen atoms. You get that? You have to be in the world of number of particles. And what four-letter word means you're in the world of number of particles? Mole. If you ever want to go in the world of number of particles, you have to get in the mole world. All right. Now, you okay on this so far? So let's try it again. Let's go up here. How much would one water molecule weigh? What is the weight of one water molecule in the little tiny world? How much? 18 what? Excellent. Now, let's jump it up. I'm going to give you more than one water molecule. I'm going to give you this many water molecules. I'm going to give you a mole of water molecules. Wow. That's a lot of AMUs. You're right. But there's something special about that number. If I give you a mole of water molecules, whoops. I'm sorry, I forgot my 2 here. That's my fault. I forgot I had a 2 here. If I give you a mole of water molecules, how much is that going to weigh? 18 what? Oh, ho, ho, ho. Now, why is this important? Why is this important, okay? I can't go into the little world and count out 10 hydrogens, and I can't do it. But you know what? If I go over that cabinet right there, and I go get a graduate cylinder, and I put 18 grams of water in there, you know what's in that graduate cylinder? You know what I know is in that graduate cylinder? And I never counted them. You know how many water molecules are in that 18 grams? How many? 1 mole, which is how many? If I said how many is a dozen, would you ever tell me it wasn't 12? So in chemistry, if I say a mole of anything, don't ever tell me it's anything except how many? 6.02 times 10 to the 23rd. So if I went over there and got that graduate cylinder and I put 18 grams of water in there, I can tell you right now, you know what's in there? 6.02 times 10 to the 23rd molecules of water. You never counted those. Yes, I did, didn't I? Counted by what? I counted by weighing them. Because in water, 18 milliliters of water is 18 grams of water. That's just for water. If I know how many grams you are, I can figure out how many particles you are. And so in the world of chemistry, they said, man, I don't know what the formula is, but I know that this many grams of this combines with this many grams of that. I do know that. Man, if I could just get in the world of number of particles, I could figure out how many carbons combined with how many hydrogens. See that? And so the mole concept was huge. It was a huge breakthrough in chemistry. I can finally visit the world of number of particles. I can count atoms. I can count molecules without counting them. I can weigh them. Just like the jelly beans. I'm not going to sit there and count out 1,000 jelly beans. If I put that many grams on there, it's going to be around 1,000. Pretty close. All right, did I lose you? I wish somebody would have given me a lesson kind of like this. You're going to hear it again. But I wish I'd had a lesson kind of like this because I really didn't understand what a mole was. I remember I was supposed to memorize something about a mole. I never understood the idea of a mole. And so if the ratio, if this guy's 18 AMUs in the little world, and I give you this many of those, it's going to be 18 grams. And you know what? I can't do chemistry with AMUs. But do you think I can weigh out 18 grams of water? I can do that. And if I weigh 18 grams of water, I know how many pieces of water are in there. All right, are you okay? So I'm not going to use the word elam. I'm going to use the word mole. That's what you should know, what a mole is. Are you sure about this? Okay, let me give an example. Let's do one more, okay? Ready? 1 mole of CO2. Okay, sorry. All right, answer these two questions. What is the weight, what is the mass of 1 mole of CO2, and what is the mass of 1 molecule of CO2? Little world, big world. Let's see how you do, right? And by the way, the reason that number is not a whole number is because of isotopes. You get it? So in a bucket of water, not all the hydrogens are equal 1, but most of them do. How do I know that? How do I even know that most of the water molecules are 1? Because somebody with a really, really expensive equipment, when they found out the average mass, what's the average mass of for each hydrogen atom? It's really close to 1, isn't it? There must be a whole lot of them, like 99.9% of them must weigh 1, and then maybe a few of them, maybe a few of them weigh 2, and I'll bet not hardly any of them weigh 3. And that's why the average is not a whole number. See this guy here? Do you think, are there any oxygens who weigh 15.994? Yes or no? No. Were there any jelly beans with a mass of 5.011? No. But the average mass of a jelly bean was that, wasn't it? There are no oxygen atoms with that mass. Are there some with 16 things in a nucleus? Oxygen 16? Yes. Is it possible there's an oxygen that weighs less than 16? What do you think? I'm asking you to think here, right? Do you think there's an oxygen that weighs less than 16? And if somebody right now in your head, you have a little coin in your head, you're flipping it. Yes? No, don't do that. I want you to think about it. Do you think there's any oxygen atoms with a mass of less than 16?
Yes.
Raise your hand if you have a definite answer. Don't say what it is. If you say, I have an answer, I'm not going to tell you what it is. Raise your hand if you know. Now raise your hand if you say, I'm not sure. Okay, let's try this. You play baseball? Let's say your batting average is 333. Okay? And I happen to know that the first game, you had a batting average of, we went 1 for 4. So your batting average was .250. But during the season, now your average is 3.333, which baseball players don't like to tell you .333. That sounds too small. So they said 333, but it really means .333. And that means you got to hit 33.3% of the time. Oh, is that what that means? Yeah. Now, let me ask this question. If I know the first game your batting average was .25, did you ever have a game that was higher than .333? You had to. You had to have one higher than .33 because the average is what? .333. Look at this right here. If the average is 15.99, do you think there's no oxygens less than 16? How do you have an average less than 16 unless there are some oxygens less than 16? I'll tell you right now, in chlorine, there's only 2 isotopes of chlorine, and the average is about 35.5. What's that tell you? There's only 2 isotopes, and the average is 35.5. What does that tell you? I'll bet if I sampled 1 million chlorine atoms, I bet about half of them would be what? The average is 35.5. There's only 2 isotopes. What do you think? I'll bet half of them have what mass? Say it. Say the number. 35. And what's the other half? 36. What would the average be? 35.5. Oh, that's the reason that number is not a whole number, because there are isotopes. Now, my discussion here, though, let's not get into isotopes right now, okay? So you probably used 12 for carbon, is that right? And did you use 16 for oxygen? Okay, so you haven't said anything all day, have you? Okay, and any of your classes say anything all day? Okay, here, what do you have for this? What's the mass of 1 mole? Man, that's a lot of carbon dioxide. What do you think?
I'm not sure if I can tell you the molecule.
What is it?
I'm not sure about the mole, but I can tell you the molecule.
But how much does this weigh? How much does a 1 mole of carbon dioxide weigh?
6.02 times 10 to the 20.
Okay, now, to put the brakes on that, and then forget what you just said. Now, let's call somebody. Danielle, what do you think the weight, what's the mass of 1 mole of, do you want to do this one first? What's the mass of 1 molecule of CO2 in the little teeny tiny world?
I don't know.
Okay, let's take a look. In the little tiny world, let's start for carbon. Each carbon has a mass of what? 12 what? 12 MUs. And each oxygen is how much? So what's the mass of 1 carbon dioxide molecule in the little tiny world? 44 what? AMUs. Okay? Now, let's go again. Elizabeth. Let's have Elizabeth. What's the mass of a mole of carbon dioxide? Man, I gave you a lot of them. I gave you a lot of them.
Is it 44 grams?
Yes, yes, yes. Now, here's what I think is amazing about God. Here's this little world that I can't really visit very easily at all. But it says God gave our brain the ability to figure out things like this. And here's what he said. If you can tell me that 1 molar molecule is 44 AMUs, then I'll tell you what 6.02 times 10 to the 23rd, that's going to be 44 grams, isn't it? And so here's what he did. Whatever is happening in the little world, I'll magnify it for you in the mole world, and you'll be able to do experiments in that world. All right, very good.